Hi, welcome everybody to the using the IP protocol suite for deep space networking TIPTOP presentation. I'm Nalini Elkins with Industry Network Technology Council. I hope you can all hear me okay. Please put something into the chat window if there's any problems with sound or anything. Okay, thanks. Let me just check the chat. Okay, so this presentation is being presented by Industry Network Technology Council. We are a nonprofit, and one of our purposes is education, in particular about standards. And today there's some sad news about Fred Baker, who was one of the founding board members of INTC, but I know Mark will be talking about that. So we partner with the India Internet Engineering Society, which aims to bridge the gap between India and the internet standards, basically capacity building in India, as that is one of our biggest and growing economies. We've had a number of webinar series with INTC. We spent probably 2 or 3 years on IPv6. And then quite a bit of time, probably a year on security. This year, we are taking on new work. Last one we did was on AI, and then now Mark will be talking about the deep space. We've had a number of grants from Aaron and also APNEC for training and various deployment and research. Just a couple of words about me. I'll keep it really brief. I'm basically a software developer. I write code all day. But let's hear from Mark. Mark has been involved with the IETF for many, many years. He has many RFCs that he's written. He's co-chaired a number of different groups, been a part of the IAB. And today, we're going to be very interested to hear all the stuff he's doing about deep space. So that is, I'm very excited to hear from him. If you have any questions, do let us know, but I'm going to stop sharing now, turn it over to Mark.
Good morning, good afternoon, good evening. I'm just trying to share my screen. Where's this presentation? Do you see the presentation or the full screen?
Yeah, you might want to put it into full screen mode.
Okay, so you don't see, yeah, okay.
Yeah, I think you put it into, yeah, we see the current, current and next. You want to put it into, so we see it in presentation mode.
How about that?
Perfect. Once you go back a screen then.
Yeah. Works?
Perfect. Okay, I'm going to go on video and very excited to hear from you.
Thank you very much. Dhruv contacted me a few weeks ago, well, probably more a month ago, about presenting what the TIPTOP working group is being doing. And so that's the main purpose of the presentation. We just heard this morning that Fred Baker passed away. So kind of a sad news. I started to be more really involved in the IETF about the time, during the time he was the IETF chair. I was involved at that time for, deploying IPv6. So sad news to hear. So this has been said. I'm presenting this often to different type of people, sometimes, because it's kind of a bridging two ecosystems, essentially the space communications people and the internet engineering people. So this presentation assumes some knowledge of each because we don't want to go too much into the basics, but not too much. So hopefully you'll get the right level. For example, sometimes for space people, I make a few slides on what is the quick transport in this context. Here, I'm not doing it, but often discussions actually are about to understand each other and essentially, for example, understand the keywords of each ecosystem. And sometimes we even face the problem that we are using the same keyword for very two different purposes. And L2 is a good example if its usage in each ecosystems. Just to make sure, this presentation is only my personal contribution and opinion. I do not talk on behalf of the IETF or the TIPTOP working group. So what's the TIPTOP working group? So TIPTOP is a keyword suggested by Wesley Eddy, and it's expanded to taking IP to other planets. So in a nutshell, and that's really a short version to give you the perspective to start with, the nutshell of the charter is that given the delays and disruptions involved in space communications, we need to engineer, IP-based internetworking and support IP applications end-to-end. So essentially, the IETF, all the protocol suite, but in the context of space communications. The protocol themselves can be profiled, but the charter prohibit working on new protocols. The target scenarios are Moon and Mars and deep space. What is out of scope is the bundle protocol, and I'll come back to it later, and anything around the Earth. So LEO, MEO, GEO, low Earth orbit, medium Earth, and GEO scenarios are out of scope. This is kind of done or done elsewhere. And obviously we'll need to coordinate and collaborate with the different space organizations and within the IETF. The current work items is defining essentially what is different in space than normal internet, key characteristics, use cases, and requirements, the differences that apply to the IP architecture, recommendations for existing transport protocols, starting with QUIC, and considerations for DNS. But why, before going too much into the details, why are we doing this? Well, the first order question is, do we really need a network in deep space? Well, it has been proposed to use a network in deep space for 25 years or so, but even more nowadays, where for Moon, the current environment or the current direction is to, instead of having space agencies doing their own, launching and sending their spacecrafts to Moon, for example, we're more in the commercial environment. So it's similar to internet, where before it was more government funded and within, a smaller set of people, and then it opens up commercial. So we're seeing the same thing in space, where we'll have commercial providers doing, offering services, communications, networking, any PNT, what we call PNT, which is about position and navigation and timing. We will have multiple users and commercial users that may do various and offer various services on the Moon or Mars. We'll have various assets. We need them to share links and utilize as much as possible the full the links. So And this is compared to what has been done since the beginning of the space era, where link usage was planned and is still planned and dedicated to single mission per communication window. So for this link, for that time, it's for you. So clearly we need to build a layer 3 network end-to-end. So the choices of the network layers above CCSDS, CCSDS stands for Consultative Committee for Space Data Systems. These are the standards for link layers in space. You know, in some ways similar to Ethernet or, you know, frame relay or all those layer 2. We have two choices for network layer, bundle protocol and internet protocol. And I'll come back with only 2 slides on bundle protocol to, you know, set the stage. But the main purpose of this presentation is IP. Terminology, deep space in ITU definition means doesn't include moon, but we're kind of including moon in general in this presentation and in the work of the TIPTOP working group. So what are the main challenges for networking deep space? There are many, many challenges in deep space, and you know, just landing something on moon is difficult, as you may if you see what's going on in the industry and the landings that were tried over the last years. But so overall, you know, we could discuss in length for all the challenges, but let's focus on what has an impact on networking, which is above layer 2, right? So there's a lot of things in communications in layer 2 and layer 1 in space that will be handled at that level. What we really care about mostly is the long delays. So compared to internet, long delay, one-way delay to moon is a bit short of 2 seconds. And Mars, depending on the positions of 2 planets, is 4 to 22 minutes. So the RTT is kind of the double. So an RTT, one RTT for Mars, the worst case, is 44 minutes. You know, it's kind of simpler to fix because you roughly just, you know, adjust timers. Whatever you do in your protocol, you instead of expecting something within 100 milliseconds, you expect 22 minutes or more. But one consequence is you cannot expect immediate reaction to events because the delays. What is more complicated, in fact, is the intermittent communications. And if you see the drawing on the right of the screen, from the end-to-end point of view, the round trip time is pretty large, but more importantly, it's very variable because it jumps, right? If you look at the drawing, the orbiter, when it's behind Mars, doesn't communicate anymore with Earth. So you'll see a kind of black hole of communication, right? And then it's only when the orbiter comes back in the line of sight for Earth, similar to rover. And then if you have multiple rovers in different places, and so all this makes communications going, and then out of the sudden, no communications. So a mechanism anywhere in any protocol, assuming a relatively stable RTT, will just fail. Well, RTT is not stable on internet, right? Sometimes congestion happens, but then recovery kicks in. But there's an immediate and fast reaction, which is possible on internet, which is not the case in space. So you need to be careful. The whole thing here, those challenges are under an umbrella of a name scale delay, which was called initially delay tolerant network. And then it became delay and disruption tolerant network. DTN can be delivered using BP and IP or both. Obviously, we're talking about IP. So if you look at the network architectures that in communications for Lunar and Mars, the IOAG, which is the Interagency Operations Advisory Group, which is the kind of a collection of coordination of many space agencies. They delivered the architecture documents for Moon and Mars, and NASA has its own for LunaNet, and ESA has its own for Moonlight, called Moonlight, and the reference are on the bottom of the slide. So the architecture is that they expect that on celestial body surface, such as Mars or Moon, and around, you'll have a 3GPP network, so 4, 5, 6G, and Wi-Fi, creating an IP network. The orbiters around celestial bodies will carry both IP and BP, and the CCSDS deep space links, for example, from Earth to the orbiter on Moon or Mars, will carry BP and IP. The LunaNet interoperability specification at NIS, actually, which is a public document, defines IP and BP as network layers. So therefore, you can see the following regions, right? So the Earth, internet and private networks are running IP. The deep space links to the celestial bodies are using CCSDS link layer that can carry IP or BP. The Moon surface network is running IP over 3, 4, 5G, 6G, and Wi-Fi. The orbiters are around celestial body can run BP and IP can do IP or BP forwarding. And within the spacecraft, typically there's a typical internal IP network. So if you see, as I try to highlight, is the fact that there's a common networking protocol used everywhere, which is IP. So IP then everywhere, right? The good part is that if you have a single network layer, it makes everything more simpler and way more cost effective. You don't have complex gateways between protocols which are more fragile and brittle. An application, if you think about an application, you only use sockets or a single interface. You don't have to think about two different network layers that are very different. If you have a single network layer, you can view and manage the whole network from any vantage point, and a lot of advantages. So why not BP, bundle protocol, right? So what happens is a study was made by GPL engineers and Windsurf early 2000, actually a couple of years before. And at that time, if you remember, if you were involved, TCP and UDP were the dominant transports. We had chatty protocols and roughly low usage of IoT. So they concluded appropriately that the IP suite was not suitable for space. So we need something different. Therefore, we designed a new networking stack, bundle protocol. Bundle protocol, to me, and that's my personal opinion, has many issues. One of which is it doesn't have any transport semantics. I'll have one slide on this, and then we'll forget BP. But since 2000, we have the quick transport, which is really modern, agile, configurable, efficient. It does one handshake, one RTT handshake for both the connection establishment and the TLS, the security. It's user space, correctly managed mobile. We tried many ways to handle mobile at the IP layer and really the right places that transport. It has all encrypted end-to-end transport, and you can have all unlimited request response streams, applications over possibly very long lasting connection. So this is very different, and is a key component of the work. The other thing is we know how to handle IoT, and IoT means essentially low bandwidth, small memory, slow CPU, energy efficient devices. That's pretty much the same requirements as space, right? So if we can do for IoT, it's essentially the same requirements. So we did with a team of people a reassessment of IP in space in 2022, and here we are. So the first question usually I'm getting for this presentation is, how do they compare? Obviously, we could do a whole presentation by itself, and please be careful. This is just an overall idea. If we want to debate, I'm happy to do, but I'm getting every time, which makes sense. how do they compare? So here's the one slide for the comparison. And instead of going into too many features, I wanted to kind of describe a bit the design of the architecture. And here on your left is an extract of Steve Daring plenary presentation on IP hourglass that makes the case of internet, not IP internet layer, with global addressing, virtualize the network to isolate any kind of end-to-end protocol from networking details or changes, different link layers, maximize interoperability, minimize the number of a service interface, exactly what I was saying just a minute ago. Narrow internet protocol, so very thin, the least amount of network functionality to maximize the number of usable networks. And I would say it's a layered architecture. Each layer does its job and hopefully well. And intermediate nodes, because it's a very simple, layer 3 protocol, they can forward very fast, but having limited functionality to process and implement, right? On the contrary, BP suite do not have a transport. Therefore, in the BP protocol suite, there's no congestion control, no flow control, no reordering or duplication recovery, no end-to-end loss recovery. The only thing that on the loss side is they design a hop by hop. But the problem is if one hop goes down and kind of drop the packet, then the packet, or actually the bundle at that time, the bundle just is lost forever because the endpoint don't have the copy anymore. And there's no transport security TLS. BP suite has very few applications. And one of the reasons is developing a BP application, and I try that, essentially requires to re-engineer transport, right? So you have to, handle congestion, flow control, reorder, all those things has to be done by the application, and it's not standardized. And from the design point of view, BP engineering essentially is trying to make the network layer fatter by adding more features into it. And one example, the recent example, is adding bundle sequence numbers and extension blocks, or headers, extension headers, if you want. And that's for kind of starting to look at the transport, kind of identifying a sequence number so you know which one you lost, right? So another thing is, by design, is BP nodes have permanent IDs. So this is our typical IETF discussion on location versus, permanent ID. And so the drawback of this is there's no possible way to aggregate routes. And mobility means then if you move to another place, bundle protocol agent, move to a different place in the network, then you need to somewhat advertise your node location to the whole network, or at least to your peers. So anyway, so this is a short summary of, difference between BP and IP. So what needs to be done on IP suite for deep space? Obviously, this is kind of a simple, but it concentrates you to the key points. If you think about the IP protocol and UDP and even IHTTP, they have no notion of time. There's nothing to do. An IP packet or UDP datagram or HTTP request could be for a year, right? There's no, within the protocol, there's nothing here. HTTP has a few headers that are related to time, mostly about caching or life cycle things, but if you don't use them, then an HTTP request can be in flight for a year. However, so what you have to do is for forwarding devices that are facing intermittent links. So for example, if you remember the small drawing, the forwarder that is on Earth that is facing talking to the orbiter, and sometimes, oops, the orbiter is out and then it comes back, then in a typical IP forwarder sense, you will lose the route to the destination because the link is down, and then you will drop the packet. In space, because you expect those to happen, you store the packet at the forwarder, but only the forwarding devices that are facing intermittent links routers behind or routers elsewhere don't need to do this. It's only the forwarding devices facing intermittent links. Storing packets is not difficult to do. We did it 500 lines of C code, and we did another version on Rust. It's not a big thing to do. Obviously, our implementation is not, for the commercial hardware vendors will do way better than us. But just to tell you, it's not rocket science. We don't need to do any storage of packets on the surface of a celestial body where there's a 5G or 6G network or Wi-Fi. We don't need to do storing packets if they are the orbiters or the gateways are layer 2 because they don't know about IP. They just forward based on their information like a bridge, right? Like a switch, a layer 2 switch. And that's currently what is being done by the Mars orbiters. There's 4 Mars orbiters currently, and they do this. Actually, they do this at layer 1, but roughly they store packets, but they store bits, right? They don't know about IP. And obviously the end nodes that are not forwarding don't need to store. So only a space edge, essentially, those forwarders has to store packets instead of dropping packets. Second is if you need to deliver end-to-end reliability, you need to configure the transport based on a deep space profile. So you need to do the right set of values for timers. One way to do it is that the intermittence is not directly seen by the transport. It's just long and variable delays. Well, just that sentence, obviously for people, experts in transport, there's a lot to say about it, but let me be simple at this point. And if given that the RTT is actually changing a lot with large values and small and stuff, so you need to not rely on typical RTT for internal calculation. So on the application side, you don't have to do much in the sense that it has to be an asynchronous design, which is typically what a good web app is currently doing. And adjust timers, obviously. You don't expect a response within a second. It will take more time. Having said that, that doesn't mean that a typical web application will be ready to go for space because obviously there's a lot of assumptions about interaction, right? So be careful. And we're not envisioning, we're envisioning mission and science-based applications, not typical web applications. So this is kind of the deep space protocol stack, IP protocol stack. You have on the bottom the layer 2, which are CCSDS space links, Wi-Fi or 3GPP or any kind of Ethernet 802.11 or 802.3. IP, UDP, TCP doesn't work in this environment. Over UDP, you could have CoAP, which is an IoT-based protocol, similar to HTTP semantics. You may be able to run NTP, SNMP, media, apps over UDP. You can use Quick, which runs over UDP, which includes TLS. And then over it, you can use media like Mock. You can tunnel like Mask. You can have apps over Quick directly, or you can have apps or media over HTTP over Quick over UDP. So that's kind of the overall protocol stack. Now, maybe in your mind is, does IP actually work in deep space? Well, let's put in test. Moon is like 1.5 seconds, so it's kind of too easy. Let's do Mars. So here's a simulation of Earth to Mars via an orbiter. The simulation is an HTTP over Quick request and response. The Quick stacks, there were 2 different Quick implementation used. Obviously, as I said, you set the proper timeouts, the proper values. And for this simulation, we use where the 2 planets are nearest, so 4-minute one-way delay. By the way, if you ever do those simulation using TCNetM, which is on Linux, be careful, because before they were not supporting they were not supporting delays more than 270 seconds. But after contacting the maintainer, he made a patch, and now you can essentially simulate to multiple galaxies away. So it's in this simulation is a dark Earth, Mars orbiter, and Mars asset. There's no intermittence. The HS here means the one RTT handshake with quick, and then you do the request and response, and then you do connection close. Obviously, connection close here is not needed in reality, because you can keep the connection forever for additional requests. So obviously, I know that you cannot look in details about the Warshak, but I guess you could look at it offline. So this was without intermittence. Does that work with intermittence, such as orbiter with blackout timeouts? So same kind of environment, but now the orbiter has an intermittence of 1 hour 2 times. We simulate 2 times, and we send one request every 15 minutes. So some will pass, then some will happen to be during the intermittence. And what happens if you look at the right side, that when there is orbiter is no more available, then we will be, or it doesn't see the asset, then the orbiter will store the packets received and will wait until the asset is visible, send the packets to the asset, and maybe the asset is seeing the orbiter, but the orbiter now doesn't see the Earth, so it's the storing packets. So I guess you understand what I'm meaning here is that we're demonstrating storing. And so again, this is the Warshak, the TCAP shown with Warshak, and you see on the left, the arrows on the top showing every 15 minutes sending a request and continuing. But then in the middle of the slide, you'll see that if you look carefully, that there's no reply back, because the orbiter is actually storing the packets. Well, I showed a few minutes delays, longer delays possible. Well, we tried in simulation an HTTP request to Voyager, 18 hours one-way delay, direct linked to the Voyager node, HTTP over quick, and it just works. You just need to make apply the right values for the timers in the quick establishment connection API. What about packet loss? Let's try 5% packet loss over a long delay. So put delay of 24 hours and 5% packet loss. So what we did here is we essentially repeat 10 times HTTP request and response in the same connection. Total time was actually the same as without packet loss, because over the time of the whole simulation, the packet loss was randomly done on the server side, and then the client detected and then retransmit before the whole set of requests and response were done. So in fact, and we didn't try to do this, it's just what happened. So, but the key point here is quick recovered successfully, and all data end to end were properly sent reliably. Quick connection a quick connection in general may last seconds, minutes, hours, days, weeks, or months. There's no limitation on this. And within a quick connection, which is really new here as a transport, is you can have multiple requests and response carried out by either the client or the server or both, right? They can initiate each way. They can be direct directional or unidirectional. You can have multiple protocols or applications running within the same connection. It's like a virtual pipe where you can have HTTP request and response, but also video streaming coming from one side, network management queries whatever. That's very powerful for, especially for space, because for space, given that the connection establishment can take like 40 minutes, you don't want to do this all the time. So you would highly prefer to get a connection done initially as soon as possible, then keep it quote unquote forever or the most longer time. But you know, if whatever reason the connection dies, then the marginal cost is 1 RTT and you're back on track. And if you don't need reliability, then just use a pure UDP. What about network management, QoS streaming, and the list can be, you know, can grow whatever. The good news here is we have a whole bunch of protocols and applications protocols that are available in the IP suite. The question is more which one works, which one needs to be profiled, which one need to be, you know, modified. So, for example, for network management, we simulate SNMP, and SNMP get and SMP get over UDP just works fine, no problem. You just need to set at if you use the our old friend SNMP D, and so in SNMP get, you set the timeout properly and it just works. Or you can use netconf, resconf over quick. Resconf being HTTP can run over quick. Netconf directly over quick is a draft that is a working group item of the netconf working group. So that's a possibility here. QoS, we can, you know, use our whole IP QoS traffic engineering toolkit. You can, you know, work based on service destination address, diffusers. Oh, sorry. That was diffserv marking, port service available, all the toolkit. Naming, you can use DNS, but be careful because you don't want to have DNS queries going back and forth on the deep space thing. So you'll use DNS locally on the celestial body network or on Earth, and then you make sure that you synchronize the you know, whatever you know, architecture or deployment scenarios you're using. Make sure that the DNS queries don't go through deep space because they will take too much time. We have emergency messaging is key for space, for search and rescue, for anything about this. So we may be able to reuse this framework. We have time distribution. We may use NTP. Hourly simulation seems to be working for NTP. But more work has to be done. We're currently looking at this. And we could do media streaming over RTP, HTTP, media over quick or everything. So it's just a small list, but the key point here is we have a whole set of protocols that can be reused and needs to be verified or assessed for their use in space. They may not be possible, you know, as is. One thing about possible deployment scenarios, this comes back again and again. We can do end-to-end. So for example, an application on Earth and then through the whole links and everything to an asset, a rover on the moon, or we can do a proxy-based architecture. And one architecture that has been said many times is a space edge proxy. So the last forwarder before going to space and the first forwarder on, for example, moon that receive from space, those act as proxy. That could be at different levels, right? Transport or applications or, you know, whatever. And then each proxy handles has two legs. One is on the surface side, which is typical standard body, you know, high speed, well-connected networking. And then on the underside, on the deep space side, then it knows more about specific of deep space, may even include knowledge of intermittence, right? Those proxies may know, well, I'm expected that the link to the orbiter will go down in a minute, therefore I'll start doing something, you know, storing or whatever, or signaling back to the other guys, pays down, I'm not able. So those kinds of concepts can be, think of. We haven't worked on this yet. So I hope you understand now why we have a working group in the IETF. Again, I'm just repeating the charter here, saying, given specific of space, what we need to do for the IP-based protocols. We have few work items at the current time, define the specifics, what needs to be done, in terms of the RP architecture and protocol profiling, transport protocol profiling and consideration for DNS. Timeline for the working group, we started this reassessment work, so prior to the TIPTOP working group a couple of years ago. Deep Space informal mailing list was started the summer 2023. We had about a year of informal Deep Space side meetings. Informal, we talk about problem solutions, simulation results, COAP, SHIC, which is header compression, SRV6, quick profile study on Mars orbiters, rovers, and termitants. All this is available if you're interested at this link. There's last fall, we had at the Dublin IETF, there was a working group forming BUFF presentations from or about from China Space Agency, KDDI, a provider in Japan that is planning to offer services, communication and network services on Moon. NASA, about NASA LNIS and LunaNet plans and proposed architecture and quick profile. Working group was formed in February 2025. The Deep Space name was not agreed. TIPTOP name was a suggestion from Wesley Eddy. And I've been told by Sylvia Hagen that TIPTOP means perfect in German. So I don't know if it's a great coincidence or too difficult expectation. At that time, the working group was started and chaired by Padma Pillay-Esnault. I've been named the technical advisor and delegate, and our director is Eric Vink from INT. First meeting of the working group was in Bangkok last spring. Co-chair was Zayed, and we talked about use case architecture and quick profile draft. The other topics were pushed for because of lack of time, and we plan to have a second meeting in Madrid, ITF, next ITF. If you are more interested in documents and what's going on, we have those on the right are the ones from the data tracker. None of these are currently working group docs yet. The use case IP architecture quick profile were presented in the first meeting. And I listed a few of additional drafts that may be of interest of you if you're interested in learning more. The first one, IP assessment, is the one assessment back then. Carles Gomez wrote something about COAP over in deep space. Christian Yutema and I work on quick in space. Tony Lee worked on addressing an address space for space, and there's work recently about quick compression, header compression from the SHIC people. Okay, and that's about the last slide I have. Well, a couple of more, but in terms of real content. So it's obviously in surface, and when I was talking about transport, this is probably where we'll spend most of the time because that's where it's, has more engineering to do, let's say. And as you may understand, but I haven't talked too much, just a bit, IP and BP designs are really different, but they essentially share very similar difficult topics, right? For example, routing on a large scale. I used to say when we will have 10,000 spacecraft all network on Mars and Moon and Jupiter, we may need to revisit routing in this context, right? Right now, it's kind of simple. We can manage with, basic stuff. But how would we be advertising changes in time, right, given delays and disruptions? How do we properly, because all those schedules of orbiters going off can be all calculated, right? So we can use that knowledge to actually do better engineering. But so where do we put those schedules knowledge, right? How do we use it? And what happens if schedules are not happening as it should be, right? And in space, this happens often. I'll give you an example. When we were looking at the MAROS data, MAROS is the Mars Communication Window Database. We saw that MAVEN, one of the orbiter, there was no link used at one of the paths over the rover. And so I sent an email to the manager at GPL, and he told me that the problem, which happens often, or sometimes, is that the rover battery was not enough high to actually do communication. So they had to forget that link window because battery, not enough energy, right? So even if you schedule that you could communicate, you may not. So whenever we input schedules in protocols or nodes or whatever, we need to be careful of not being fragile when things don't happen as it should be. How do we handle congestion, right? When typical signaling or finding or guessing there's congestion may happen kind of too late, right? When it's far away, and especially if you store packets, well, it's not really congestion as we know, right? It's kind of a variation of it. So we should not declare congestion if it's just stored, right? How do we handle, storage itself, right? To prevent full storage, and then you need to drop packets. And all these are kind of common to BP and IP. How do we properly prefetch our cache data? For example, key validation chains. If you want to validate some certificate, on Moon or Mars, you don't want to do queries back to Earth about, and do queries of the whole validation chain, right? So therefore, you need to kind of cache this. This is similar to DNS also, which need to be cached, right? So there's places where you need to, cache data. And, by the way, there's a proposal for an IRTF research group for space. So that's my acknowledgement page, which, I don't want to go through all of this, but many people have contributed. People here, not everybody, name here, not everybody agreed, but we had very good discussions. And my last slide, Internet Protocol Suite in deep space is being discussed in the IETF working group to make it work, store packets, configure transport with a space profile, and for applications, modified timeouts. URL for IETF working group, some documents, and thank you very much for your attendance.
Thank you so much,
Marc.
Marc.
Questions.
Yeah, thank you so much, Marc. That was very, very interesting. So you know what? Anybody who would like to talk, we have about 10 minutes. Please raise your hand, and let's see if we can unmute you. Mohit, maybe you can help me. But from watching the chat, it seems there's a couple of threads going on, Marc. One thread has to do with retransmission. And there are people saying that because bundle protocol is used in terrestrial cases, I think they were using like nomadic tribes and such like that, where I think that it seemed to me it was like the hop by hop acts were pertinent. If whoever it was, if any of the people interested in that conversation would like to jump in, if I'm not stating this correctly, please do that.
Yeah.
But what is your thought on that?
Since we started to do this work, all the time I was refraining, trying to kind of compare the two and see. I think they're two different designs, and there's pros and cons in each design. But every time, and you see now that people want to talk about bundle protocol design, and so we had discussions on maybe writing a draft on comparing both in details, and we'll probably take like a whole presentation by itself. So so back to retransmission. So when we started to look at Quick, it was surprising that, because it's a really modern design, that we were looking at, okay, how does that work? And then, well, it actually works. The way they would design it was almost like the right way you could think. And I'm not a transport expert, so I'm kind of a amateur here. But so, for example, just to go into one example of Quick, again, we could have a long conversation on it, and I expect to be soon in the working group. So if you're interested, please come. Quick, the way loss is actually handled is, let me, well, I don't know. I guess I probably unshared, or did I share?
No, we can still see your screen, Mark.
Okay, whatever. So Quick machinery for loss detection is based on ACK, and one way is that there's so if you have received an ACK for a packet which should be later, or actually later than one which you don't have, and then you wait for a certain number of packets not received, and the typical number is 3. And this is like based on 40 years of experience with transport to TCP. Then you declare it kind of lost, and then you retransmit, right? So that's kind of an example of Quick machinery, which not depends on time, but more on the behaviors of acknowledgements, right? So that's the example I showed of the simulation of packet loss was exactly that, because what happens is the Quick machinery found that, oh, okay, this one I haven't got hacked, but I received a few packets since then, and they're all fine, so declare loss, retransmit. Nothing about time. The second way that packet loss is done in Quick is, or therefore transmission, is with time base. And then that's where, and it's kind of not the second way, but the other way. And then that time you need to be careful of setting the right thing. And it's essentially based on calculations based on RTT. So back to the presentation I made a while ago, be careful because the RTT can change a lot. So things like that. Third thing is that Quick actually do not resend the packet. It actually, if you read RC 9002, you'll see that it actually is smart, because Quick is actually doing frames within packets, and the packet as you lost, you don't necessarily need to repeat everything. So you will actually create a new packet, but only with the thing that really need to be sent. So it's very, very efficient. I don't know if I answered the question, but we can spend another hour.
No, thank you, Mark. That's very, very interesting. I mean, I think the whole thing that what you're discussing about selective ACK, and then the way even RTO and RTT, all that works in TCP, very similar questions that we've all been struggling with for many, many years. And of course, there are applications that retransmit too quickly, overly reactive, and causes more problems if you're overly reactive.
Yeah. And continuing to what you just said, here's the thing here. Please do not try quick, non-configured quick, stack or client over long delays. It will not work. So
Well, Jannah Iyengar. Jannah he spoke to us about Quick. I think it was maybe last year or something like that. And what he was saying is in India, is a lot of the villages, people doing streaming video in villages. He says Quick is so much better. He says it's recovery from loss much better, which makes me think, but actually, to get back to the other question, fundamentally, I think the question was about retransmitting over multiple hops. But now I am not getting my head around what are these multiple hops? Like, do we actually have like multiple routers in space, or is it a point-to-point link? You see my question?
Okay, good. Yeah, good point. Most are point-to-point links. They may have multiple hops, but I think what you're asking here is that, remember the slide I made about, kind of a IP hourglass and BP, and, again, my opinion, that BP is more kind of fatter because it includes more stuff within the network layer, right? So the way BP design is to really there's no notion of connection or state between endpoints and stuff. There's nothing about that. There's no transport semantics. So what happens is really kind of an up by up thing. So in BP, there's an optional service or feature which is called custody. So what happens is the previous op having a bundle send the bundle to the next op, and then the next op will kind of tell the previous op, okay, I got it. I take custody. Over, right? And then the previous op can just release the memory of that bundle because it's guaranteed is there, right? So that's kind of a design that is up by up, right? What I'm saying here is that IP has a different design, which is IP itself kind of assumes that the network below can be unreliable, and it doesn't matter. You losing a packet is not a big thing, and then you rely on the transport to actually recover whenever you need to retransmit that data, right? So, and that's something I said a few minutes ago in the presentation, is in some ways the transport becomes I think, to me, my opinion, the transport should be essentially completely unaware of intermittence or anything happening, right? It's end to end. The other party didn't receive something, well, we'll retransmit. And the good thing is TCP we would need to redo TCP again if we want to do TCP over space. Well, why we would do this, given that Quick is actually, kind of a summary of all the experience we had for, 40 years. And, its mechanics is pretty well for that use case. I don't know if I answered your question.
Great. That's great. No, this was just a wonderful talk, Marc. And you really appreciate you coming on and spending your time with us. That's great. And guys, all the people who've sent all these wonderful questions, I encourage you to join the working group email list, ask those questions there, and participate in that working group. And do please, if you have other questions that you want, please go ahead and send them to myself or Marc. And I'm sure that Marc would be happy to answer and discuss more. So again, thank you all so much for joining. And I believe next time we'll be discussing one of our board members from Akamai will be talking about some of the new things going on as far as the whole CDN world. And if you guys have any ideas for more things we should be doing, please go ahead and send me or Praneet or any of us an email. And thank you again, Mark.
Sure, thank you.
Great. Bye.